Yes, gradient, Jacobian matrix and Hessian matrix all in one video. It's basically about partial derivatives and their representations both for the first derivatives and for the second derivatives. I'll start with the gradient. Here we have a function that outputs a scalar, so a single number. When you take the partial derivatives, partial f with respect to x, then we get 2x, and partial f with respect to y gives us 2i. That's supposed to be a y. And if you now, for example, use the nabla operator on fxy to get the gradient, then that's 2x, 2y. Here is the gradient. Now we have first partial derivatives here because it's a function with two arguments, differentiated with respect to x and with respect to y. Here we have a vector-valued function. Yes, that means we have two functions represented together as a vector. And that's why we now need the Jacobian matrix when representing the first derivatives. Yes. That means if we now take the partial derivative here, yes, we are now taking the partial derivative of f with respect to x. Yes, so here we differentiate the top part. If we focus on the x, we get 2x, and down here differentiating y times x with respect to x gives y. That means we have a vector and partially differentiated. With respect to y, we get 1 up here and x down here. And the representation is now in the form of the Jacobian matrix of f, which would be 2x I and 1 and x, Jacobian matrix. You could also apply the Jacobian matrix here. That would then be a row vector. That would be for this function up here, jf equals 2x2y. I hope you can see that here, partially differentiated with respect to x, partially with respect to y, here partially with respect to x, partially with respect to y, and that's how the Jacobian matrix develops further. The Hessian matrix, in turn, for a function that yields a scalar, involves the second derivatives accordingly. That means for that I'll take this function here again. We have the first derivative, partial with respect to x, partial with respect to y, and now come the second derivatives, yes, and for the second derivatives we have partial second derivative. That's why you see the two as an exponent. F first with respect to x and then with respect to x again, so differentiated twice with respect to x. That would be accordingly. Our focus is here now. Here we differentiated with respect to x. Now if we differentiate again with respect to x, it would be 2, then take the second partial derivative with respect to y. If we first differentiated with respect to y, our focus is here. That is also 2, 2. Then take the partial derivative again. F first with respect to x and then with respect to y. Well, that's how it is. Then partial with respect to y. Yes, first differentiated with respect to x. That's where the focus is. Now again with respect to y. Differentiate, yes, that means the whole thing is a number, would be 0 and partial derivative twice. First with respect to y and then with respect to x. Yes, first with respect to y. Yes. So you can see it here now, yes. And then with respect to x, yes. And then we see here again that it's like a number, so it's also 0. And these derivatives, these second derivatives, now go into the Hessian matrix H of f, and it's structured accordingly. The second derivatives, first with respect to x and then with respect to x, first with respect to x and then with respect to y, first with respect to x and then with respect to y 0, and first with respect to y and then with respect to y, and accordingly f. With respect to x and then with respect to y 0, and first with respect to y and then with respect to y. The Hessian matrix also grows when we have multiple arguments. That was meant to be an overview. Gradient Jacobian matrix, which you could also specify here, let's say in a simplified version. But especially when we have a vector-valued function, we need the Jacobian matrix. And the second derivatives are represented in the Hessian matrix.